Hey guys, so right now I'm going to do a pitot test. Basically going to be measuring airspeed, okay? This is a pitot tube. Now while the pitot tube is in the port and it will disturb airflow, that's not really what I'm after. I'm not after flow numbers here, I'm after velocity. Where does the air want to be in the port? Because where the air wants to be determines what shape we need to make the port. We want to get an average airspeed, okay, of 325 to 330 feet per second average. So along this wall, the middle, the roof, the floor, and the other side, we want to have an average air velocity of 330 feet per second. So I've got feet per minute here, and then we'll have to divide that by 60 to get feet per second. Now this is one of the highest points in the port, because this is where the pinch point is the minimum cross-sectional area of the port. So the airspeed jumps up. But one thing you may not know is a lot of people think that air only follows the roof of the port. That is not true. In fact, this wall where this pitot tube is right now is going to have probably the highest airflow besides the short turn, which is a little bit further down, right in here. Okay, so I'm going to turn the flow bench on, so turn your volume down and just watch this feet per minute as I move around the port. Okay, and see how it changes. I'm going to open the cylinder head a little bit. Hold on just a second. Alright, that's 550 thousandths of lift, and I'm going to turn the bench on. So what you saw there was that the pinch point, the minimum cross-sectional area here, was around 28,000 at its worst point, but the average was about 26. And then the, sorry, can't see what you see. The minimum cross-sectional area back here was about the same. At its worst, it was about 28,000. And the average was around 26. So, what does that tell us? That tells us that the airspeed is really, really high. Okay, we want an average of 330 feet per second. So let's see what this is. So in the middle of the port, we were at 22,000. At the wall, we were at 28,000 at its worst, but the average was 26,000. And then on the opposite wall, we were at about 20,000. The floor, we were at about 20,000. Actually, it was more like 21,000. And then at the roof, we were also at around 21,000. So that's about 5. That's an average of 22,000. You divide that by 60, that's an average of 366 feet per second. It's too fast. Anything above 330 feet per second, you start getting beyond laminar flow and you start getting really big eddy currents and it starts getting turbulent. 366 is still feasible. It's still workable and you still can flow really, really well. At 550 thousandths lift, this thing flows 300 CFM. It doesn't go turbulent yet. In fact, I just did some changes to it we'll talk about in a different video to make it flow even more at a higher lift before it goes turbulent. So it doesn't go turbulent now until 635 thousandths of lift. But anyway, that's all part of this. Okay, so we do these velocity maps in the port. Okay, you want to get just inside all the way around, trying to make it to where the pitot tube is disturbing the air the least. Kind of walk it up the wall. And then get the middle all the way back. Work your way back until you get to the short turn. Then you want to map out your port. You want an average velocity of 330 feet per second. Okay, that's 0.3 Mach. You want that everywhere. If you can manage that everywhere, your flow numbers will be excellent. They'll maximize your flow. So you just want to keep making this larger until you get that velocity down. Now, I've gone as big as I can go on my pinch point with these cylinder heads. They're maximized. They are what they are. I opened it up just a little bit to slow the airspeed down around this turn. But if you look, so if you're looking at the port, okay, let me see if I can get you in here a little bit better. So if you're looking at the port, all right, where that short turn is needs to be at a very specific spot. You got to walk that back, lay it back. Now, it's hard to see. All right, and I can't really do this. I don't know how to do this any better, but you gotta lay that short turn back. You can't really see it very good on the camera, but sorry, I'm trying to stand you up. I don't know what you're looking at. Hold on. I'm trying to have you look at the sky. Once you get your average velocities concentrically, you want to start putting little pieces of modeling clay in different areas to try and figure out how you need to shape the port. whether you need to weld up an area or you need to start grinding on it to make it bigger. You can use things like this. This is a modified flow ball. So it's a larger one, but you can see with this one, you can start seeing, you can rub this around the corners and start seeing if pressure differential drops. If we're at 28 inches of water and I move this thing in there just like an inch and it just drops, that means there's more flow. That means something here is unhappy and you're helping it by putting this flow ball in there. That's one thing you can do. Another thing you can do is this is basically a spark plug that I've drilled the center out of. Okay, I didn't weld, I put a copper pipe in there, and you can see it goes all the way flush. Okay, and you can put this down, screw this in where the spark plug is, and you can stick a velocity probe right down the middle and see what the velocity is coming out of the valve. And that'll kind of tell you what your velocity is, where it's trying to swirl, if you have any kind of swirl in your port. And you can move it around to see what different angles of the port are doing. That's an easy thing to do. These are all methods that you incorporate to figure out what your port wants. So there's a lot of people that will tell you a lot of things about what the shape needs to be, what the short turn radius needs to be, what the math says their cross-sectional area needs to be. And while everybody has their own methods, if you can get an average velocity of 330 feet per second everywhere in the port, an average, the flow will be there. Your port will be happy. And if you can make the port larger without dropping average velocity, you're going to flow more air. Period. End of subject. This is just to kind of give you an idea of what a pitot tube is. I have a video out a long time ago, several years ago I did, on how these work, how you do the math. If you don't have one of these, I can get my flashlight out of it. This is a Testo 510i. And turn it off so the battery don't die. This actually measures the differential across my orifice plate for when I do flow testing. And you take the pressure taps off and you put it on here, and you use it as a pitot tube. I'm not going to go into how a pitot tube works. I did a hour-long video on how these things work, and how orifices work, and how you build a flow bench, and all that kind of stuff. But anyway, this pitot tube helps you map out where the velocities are, what the local velocities are, and then you just keep shaping your port until you get them all on an average of 330 feet per second everywhere. Now mine's what, 366 roughly. I mean, it's a little lower than that if you do the actual average. This is just me doing a quick video. It's a little less than that, but it's still not quite 330. I think it's 348, which is not great, but this is as big as I can make this cross section. Now the short turn is a different monster. That is so easy to screw up, and I will never say I've mastered it. But I figured out what this engine wants. But here's the trade-off, guys. Without going into extreme detail, I laid back the short turn. Okay. So from the last video, this was what it flowed with no manifold installed. Okay. That's what it flowed. It got turbulent. It really started to get turbulent at 600. And at 615, it was just completely gone. It wasn't flowing any more air. 600, it was already backing up and getting turbulent, but 310. It basically flowed the same at 550 as it did to 6, and 6 it just started getting turbulent. And then what I did was the short turn radius was 23 degrees, right? So on a small block Chevy, okay, 23 degree head. See if I can get you in here where you can see. Let me come over here. This is in line with the valve. Okay, if I put a valve in here, it would be perfectly in line. This GoPro keeps going to sleep. All right, so that is in line. So if you look, see how the short turn ends like right there? Well, what you want to do is you want to lay that short turn back. So it's 23 degrees. You want to do another 15 degree lay back. So after I did that, I didn't do that whenever I ported these originally. I did the short turn as a very smooth transition, but I didn't really lay it back much. So I laid it back. Well, see what happens to flow. It lost 9, 6, 11, 10. That's pretty significant right here, right? And the trade-off is up here. So I made the port happy at 600 and 635 thousandths. Above 635 thousandths, it goes turbulent again. And yeah, it flowed 321 CFM. That's good for a magazine article. But the problem is, look at how much I lost, an average of 10. So I gained 10 CFM up here. My lift of my cam only goes to 590 thousandths. So I'm not even really using a whole lot of this. And it already flowed at 550, 300, where am I? 309. So it was actually down at 550. All that short turn layback did was make it really happy at the peak lifts. Now, I don't have a dwell cam. It's not dwelling over the nose. So I'm not taking a huge advantage of this higher lift. But one thing I can do now is I was only lifting at 590 thousandths of lift because at 600 thousandths it was just plumb turbulent. So now I can lift it higher as long as my springs can handle it. With my coil bond clearance and stuff, I may have to change my springs, but it's going to be worth it now to lift the cam higher and spend more time up here in the higher lifts where I can really move some air. So I'm not done with this head. I'm going to see if I can gain some of this low flow back and maintain it happy up here. So I'm not done, but this is how critical that short turn is. I didn't take a lot of material off. I just reshaped it a little bit. And yes, it made it happy up here because I was at like 30,000 feet per second around the short turn peak. And now it's 26,000 on average with a hot spot at 28,000. But I brought that airspeed down. It made it happier. Still not 330 feet per second. A 26,000 divided by 60, that's still 433. So that's like 100 feet per second faster than I want it. But that's right at the floor, which is where a bunch of the flow is, but it's not where all the flow is. So it's still not a good average. It'll still average out to be less than that. But anyway, that just shows how critical shaping the port is. Getting your short turn radius good, getting your minimum cross-sectional area good. Now there is some math out there that'll help you calculate what your minimum cross-sectional area needs to be. If you want to know what mine is, it's about 2 100,000ths. So it's tight, it's small, and I could make it a little bit bigger, but short turn right now is at a slightly about the same as the pinch point. So if I slow down the pinch point, it's gonna basically pull more air in, but it could make it more turbulent. So I've got to look at that. I've got to do some math. I've got to do some math. I've got to map it out completely. Now I mapped it out completely. I made some changes. It flows more air and it's happier at the peak, but now I've lost some low lift flow. I want to gain that back if I can and still make it happy at the peak. So it's this flowing heads is it's a science. It's not every single cylinder head is going to want the exact same shape. Now there's some starting figures that those experienced porters go, hey, I know if I just do this, and this mathematically, it'll be pretty close, and then I can just start doing velocity mapping and figuring out where else I need to adjust things. And they'll do that, and they'll be very successful at it. But there's not a lot of people that do this anymore. A lot of them just do the CNC programming. You can do fluid dynamics, computational fluid dynamics, and kind of get a pretty good idea what a port needs to look like, and they just mass produce them. So, I mean, there's not very many people that still port heads by hand, but if you want to make as much power as you can out of a cheap set of cylinder heads, I think these cylinder heads cost me $1,000 for both. Back in, I think I got these back in 2015, maybe. This is the third rebuild that I've used these heads, and they've went through a couple different iterations. Now, granted, when I originally ported these, I ported them for a blower manifold that was pretty inefficient on how it flowed. So some of the inefficiencies in this port were because I was trying to crutch that. So I'm figuring out what I can do now. But now that I've done that short turn, it's picked up flow at the peak, so it's made it a little happier. I'm going to put the manifold on it and then see what the manifold does to flow. I want to see if it's still down at the low lift, or if because of the longer runner it picks up some of that and then it's happier on the top end. So I'm going to slap that on there real quick, and you know what, we'll just figure it out together. I'll stop the video and get all this cleaned up and put the head manifold on and bolt it down, and then we'll see what the flow figures look like. All right. Okay, so what you just saw was near the end of that little flow test. I forgot to start the camera right before I did the flow test, but I did 2, 3, 4, 5, 550, 6, and 650 thousandths lift. At 550 thousandths lift, super happy. You go above 500, 560, 570, 580. It goes a little turbulent and flow flatline. So 550 to 6, it pretty much doesn't pick up any flow and it goes turbulent. And then above 6, it just goes completely flat, turbulent, and flow backs up a lot. Anyway, so you could see, if you don't know what turbulence looks like on a flow bench, if you're testing at 28 inches of water and you start opening the valve more, and instead of flow drop or differential pressure, test pressure dropping, so like if this were to open up more and this goes down to like 25 inches of water, it's flowing more air and it wants more vacuum. So you turn the vacuum up. Well, if it goes at 28 inches and you open the valve more and it just shoots up like 4 or 5 inches of water, or just starts bouncing like crazy, it's turbulent and flow's actually going down. So that's what was happening here. I've got to figure out, I think what's happening here is this roof transition, because the cylinder head wants to flow a hell of a lot more. Everything seemed to be happy up until the point where I got to the higher lift. So I'm going to go back here to 550 thousandths of lift, and then I'm going to get it back happy again, and I'm going to put the throttle body on and make sure it doesn't change flow at all, and then we'll do the math and see what CFM is. So that was the first time I've actually put the throttle body on and it picked up a tenth of DP. So I actually had to lower it because it showed as a 1/2 inch of water of restriction. Then I lowered it back down to when I put the throttle body on, it was still at 28 inches and it still was 5.1 inches of water delta P across the orifice. So we'll do the math. You could see where it was starting to go turbulent. So it still doesn't want to be above 550, and I think that's that roof transition there, that sharp transition that this manifold creates. If we can fix that, I bet that'll fix the high lift flow numbers. But let's do the math and see what that is. I'll come back on here once I do it. Okay, so I've done the math, and I can tell you for sure, without a doubt, that transition right there is killing our high flow, because we picked up high flow without the manifold and lost low lift flow. Now that the manifold is on there, we picked up some more low lift flow and gave up some high lift. So I know that it's that transition there. If we can fix that transition, I think we'll not only be up on the low lift flow, but we'll also pick that back up. So here's the numbers. All right. So this is whenever I did just a little bit of porting. So we were at 156, okay? 156, 148. So we're down just a few numbers there. At 300 thousandths, we're basically the same, but 2 CFM less. Exactly the same at 400 thousandths lift, at 244 and 244. And at 500 thousandths lift, this is where we start picking up. So down below 400, it's within a few numbers of each other. And then right here, you know, what? 8 more CFM. Sorry, I'm trying to look around the camera. So that's plus 8 CFM. Now here's the big kicker. At 550 thousandths lift, with the throttle body installed on both of these, it's the same. That's 283 CFM versus 265. Wow. That's almost 20 CFM more from the short turn adjustments. Now again, I was down here at 600 thousandths lift, it started going turbulent again. So that's 261 CFM before with the sharper short turn. And with it laid back a little bit, we lost a few numbers. So that's 256 versus 261, so 5 CFM down. And then we're about 11 CFM down here. So this is what we got to pick back up. But again, I'm really impressed with how much it picked up at 550 thousandths lift. So we'll see if we can get those back. These are pretty much gonna more than likely permanently be gone, but we'll see what happens when I fix that roof. But we're on this 200 thousandths lift is very minimal impact. It does help torque a little bit. This 2 CFM is nothing, 400, nothing. And then we're just adding from 5 and 550, and it picks this 283 was all the way up to almost 600 thousandths. When it get to 600 thousandths and it went turbulent, you saw that in the camera, that's when it dropped down to 256. So it maintained this all the way up to my lift. So I could leave these heads alone right now and pull them to 592 thousandths lift and maximize the changes here. But I'm not satisfied. You should never be satisfied. I'm gonna fix that roof somehow. If I have to weld it up, I will. I'll use modeling clay at first to fix that transition and see if it's worth welding up. If it is and it picks up all that flow, then that's what's happening. But that's it for now. That's just a little introduction to velocity testing, looking at things, and then if you guys want to know more about velocity mapping, I can do a video that spends more time on it. But Yeah, so all I did was lay back the short turn radius a little bit, and slow that airspeed down around the short turn, and opened up the pinch point just a little bit on the minimum cross-sectional area, and it's picked up a ton of flow, and we're not done. So the whole goal is to pick back up the low lift flow that I lost and to maintain the new high lift flow numbers that we have. So if we can maintain those low lift flow and get up to 330 CFM at the high lift, that'll be spicy. I'll be able to, the whole goal here is, even though I'm running boost and just 1 pound of boost can make up for some of these losses, the less boost I have to run, I can make more power with less boost if I can make this flow more efficiently. So less boost, more power, and the engine's happier. I can run more spark advance without detonation on 93 octane. There's just so much. You want to make as much naturally aspirated power as you can and then put boost on it. So if I can run 10 pounds of boost and make the same amount of power as I run on 15 pounds, that requires less octane. So and I can get more aggressive with timing. So there's reasons for this, but anyway, I'm pretty happy with what we've come up with so far, and we'll keep testing.